Okay, we are going to continue our discussion about soil and talk about some characteristics of soil and some composition of soil, both physical and chemical. We're going to start out with some physical characteristics of soil, and the first is texture, and then texture is going to lead to several other types of characteristics. So soil texture is made up of 3 different types of particles, and sand would be the largest particle, silt is a medium-sized particle, and then clay is going to be the smallest particle size. And we can see, relatively speaking, what those particle sizes look like over here. The exact range for the size is not important, but we do need to remember that sand is the largest, silt is a medium-sized particle, and then clay is the smallest. We will be doing a lab where we're going to actually separate out our soil into its component particles. So how much sand is in it, how much silt is in it, and how much clay is in it. The relative proportions of those soil particles are then going to tell us what the soil texture is. So if I have a soil, say I've tested it and I've parsed out those different soil textures, and my soil is 40% sand, 40% silt, and 20% clay, we can use this soil texture diagram to determine what kind of texture it has. So the way I do this is I'm going to start on the sand side, and we can see that this arrow is pointing in this direction. So I'm going to be using this side. I go to 40, right, because I have 40% sand. I'm going to use this side of that triangle, and I'm just going to draw a line. Okay. And then I have 40% silt. So again, the arrow is pointing in this direction, so I'm going to use the bottom line. So I have my 40% silt here. I'm going to draw a line going that way. You can probably already start seeing where those lines are going to intersect. And then I'm going to look at my percent clay, which is 20%. So I get 20% clay over here. And I'm using this arrow, so the upper line, so I can draw a line there. And we can see that those lines intersect in the soil category loam. And loam is going to be our optimal soil texture, right? That has the optimal amount of sand, silt, and clay. And why that's optimal, we're going to get to in a minute. The different particles are going to lead to different properties within the soil. So I'll give you another one to try. We'll do 60% sand, 10% silt, and then 30% clay. So try yourself using the soil texture diagram to see what these percentages would give you. And you can pause the video and try it, and then we'll see what you get. So hopefully you've paused it and tried it yourself, and you should have gotten sandy, clay, loam. In our lab, we'll be doing something similar where I will give you, or you will find the different percentages of the particles, and then you'll determine what your soil texture is. The reason why soil texture is important is because different types of soil particles are going to give the soil different properties. So this table is looking at the relationship between soil texture and soil properties. And we can see here we have sand. And sand is really good at getting water into it, right? So think about like really large particles. So almost if you kind of expand this out, you think about a bucket with holes in the bottom, and then that bucket is full of golf balls, right? The water is going to be able to move through those golf balls really, really easily, right? And it's not going to be able to move through as easily as if that water was made up of really small beads. So water can get through the large sand particles much more easily because they also have large pores in between the particles. So large particles also equals large pores or porosity or spaces between the particles. So water can get in really easily, but we can see here that it doesn't hold on to it very well. So that water is going to drain out of the sand very, very quickly. We can also see that the sand has really low nutrient holding capacity. So it's not very good at holding on to nutrients, and why that is we'll get to in a little bit. But air can get in there as well, and it makes the soil more workable. So sand is good at some things, not so good at the others. If we jump down to clay, right, it's a little bit more opposite the sand, right? So having some clay in the soil can balance out having sand in the soil. So clay is not very good at water infiltration. The water doesn't get through the clay very easily, and if you think about even from pottery class, if you have a big block of clay, if you pour water on it, the water just runs off the top. But once the water is in the clay, it can hold on to it really well. So clay holds onto water well. It takes a little while for clay to actually dry out. And the clay is really good at holding on to nutrients. It's opposite the sand again with aeration and workability. So it's not easy to get air into a very clayey soil, and it's hard to work with. If you think about trying to like shovel clay, right, you can imagine that it would be really hard to work with. So sand and clay are somewhat opposite. You don't want too much sand because then you lose that water holding capacity and nutrient holding capacity. You don't want too much clay because then you lose that water infiltration and you lose the aeration and workability. Now, some people think like, oh, silt is kind of good at all of these things, or it's like medium at all of these things, so why not just have a soil that's all silt, right? There are some reasons why you do want clay in the soil, right? We need clay in the soil, especially because of this nutrient holding capacity, and why clay is good at nutrient holding, we're going to get to in a minute. But you want clay in the soil, so in order to have this optimal amount of clay in the soil, you balance it out by having a percentage of sand and then a percentage of silt. One of the important things for soil to have are mineral nutrients. So those mineral nutrients are going to be held in the soil. We'll talk about why clay is really good at holding on to those nutrients. But first, let's talk for a second about how those nutrients initially become available, and it's in a couple different ways. You can almost think about soil being built from bedrock up and then from decomposition down. So phosphate, potassium, calcium, these are all minerals that are going to be present in rocks, and they're going to become available through the weathering of that rock. So that rock is going to be really, really deep down in the soil here, and it's going to weather and it's going to push those minerals up into the soil. However, weathering alone is too slow to support normal plant growth. So we also need to rely on the breakdown and release of nutrients from detritus or dead decaying things and pushing those nutrients down into the soil. Those nutrients can then get leached or washed from the soil or through the soil as water moves through it. So soils need to be able to hold on to those nutrients until they are absorbed by the roots of the plant. Fertilizers are going to add nutrients more artificially depending on the type of fertilizer. You can have artificial fertilizers, which are these sprays and are created via factories, or you can have organic fertilizers like plant or animal waste. The chemical inorganic fertilizers, they tend to be more prone to leaching, which means that they get pulled through the soil faster. So you have to keep spraying because they're getting pulled through that soil faster, and the nutrients need to be able to be absorbed by the roots. Water and water being held in the soil is also going to be really important for plant growth. It has to be absorbed by the roots, traveling up the plant and then exiting the leaves via transpiration. There's some pores in those leaves called stomata. The loss of water via this transpiration process can be pretty dramatic depending on the plant and the climate. So we can take a look at some of this transpiration water collection in this example over here. So the capacity to be able to hold on to water after it infiltrates through is really important. If it's poor, the water is going to percolate down below the roots, and it will be harder for the roots to uptake that water. So sandy soils are going to have poor water holding capacity, where clay and silty soils, it tends to be better. So now we're getting into some more chemical properties of soil, chemical characteristics, and the first is CEC, which is actually related to the proportion of clay in the soil. So CEC stands for cation exchange capacity. And if you remember, cations are positively charged ions. So cations, positively charged ions, and we can see that a lot of those minerals and nutrients that the plant needs are positively charged, right? We have potassium, we've got calcium, we've got magnesium, right? Important nutrients for the plants, and they're positively charged. So clay particles are going to be contributing to this cation exchange capacity, the ability of the soil to hold onto these positively charged ions, these positively charged nutrients. And that's because clay particles, here's a clay particle over here, clay particles are negatively charged. You can see all these negative charges. So the negatively charged clay is going to attract those positively charged nutrients, and then some reactions at the root hair right here are going to allow those positively charged nutrients to be passed to the roots. So this chemical reaction here allows those positively charged nutrients to be passed into the root. Right? We don't need to know the details of this chemical reaction. So this cation exchange capacity is going to be a function of the amount of clay particles present. The higher the amount of clay, the higher the cation exchange capacity. However, there's a limit to how much clay we want. Right? Really, our maximum amount of clay that we want is going to be 20%. And that's because greater than 20%, we get too much water retention. That's not so good for the plants, right? Essentially, the water's holding on to too much water. It's harder for water to infiltrate into the soil. There's not going to be enough oxygen because it's not as aerated. So our maximum cation exchange capacity is going to be with 20% clay. Right? But if you have 10% clay versus 20% clay, the 20% is going to be better because that's going to lead to higher cation exchange capacity. Another chemical property of soil is the base saturation. And this is going to be the proportion of soil bases to soil acids, and it is expressed as a percentage. So this can be related to pH. It can influence pH of the soil, but it is not the same as pH. Right? So pH is on a logarithmic scale. It's unitless, and base saturation is going to be expressed as a percentage, and it's the proportion of soil bases to soil acids. And for base saturation, we want a higher percentage of soil bases. These soil bases can include like calcium, potassium, sodium bases that are going to help neutralize our soil acids and promote plant growth. Right? Sodium is the one exception to this. We don't really want so much sodium in the soil. Some of the soil acids are like aluminum and hydrogen. We do not want aluminum and hydrogen in the soil. They're bad for plant nutrition. So we want high CEC and we want high base saturation. That's going to support a high productivity for plants growing in the soil. Another chemical property of soil is pH. And again, this is different from soil base saturation, right? pH is on a logarithmic scale, right, with this being acidic, and then 14 being alkaline or basic, and then neutral is going to be 7. And when we're moving towards the basic end, we have a higher proportion of hydroxide ions, and when we're moving towards the acidic end, we have a higher proportion of hydrogen ions. So the pH scale is actually based on the proportion of hydrogen and hydroxide ions. Higher amounts of hydrogen ions, more acidic. Higher amounts of hydroxide ions, relatively, it's going to be more basic. 7 is neutral because it's H2O, which is going to split into 1 hydrogen ion and 1 hydroxide ion. So the proportions would be even. Now, soil pH is going to be really important because soil pH is going to determine what kinds of nutrients are able to be held in the soil. So we can see from right here, right, this is how soil pH affects the availability of plant nutrients. So a more acidic soil is going to hold on to nutrients like iron, manganese, boron, copper, and zinc. A more neutral soil is going to hold on to nitrogen, phosphorus, potassium, sulfur, calcium, magnesium. If you have a plant that needs more potassium and sulfur, maybe more molybdenum, then they might prefer a more basic pH over here. So we can look at different plants and we can see that their pH, their preferred pH range is going to differ depending on the type of plant. Most crops, most types of plants are going to fall around neutral pH. We can see here like blueberries actually prefer a more acidic pH because they prefer maybe more of these types of nutrients. If you're measuring your soil pH in your garden and it's not in the correct range for what you're trying to grow, and we're going to look at this when we do our soil lab, we're going to investigate our pH and think about it in terms of what we're trying to grow. If you're trying to raise your soil pH, you can actually apply limestone, which is calcium carbonate, which is going to be more basic. If you're trying to lower the soil pH, say you're trying to grow some blueberries, you can add elemental sulfur, which will bring that pH down. Changing that soil pH can then affect your nutrient composition for your soil. Beyond the physical and chemical properties of soil, another really important soil characteristic is the soil community, the actual living biological organisms within the soil. So there's lots of things that can be involved in that soil community. We're seeing this with our ecocolumns, right? We tried to put some decomposers in. There are bacteria, fungi, invertebrates in the soil that are contributing to that soil community. And there's a lot of stuff that they can do. They can consume and decompose detritus, which would release carbon dioxide. It releases water and mineral nutrients. The soil community can result in humus creation, and humus is a material that's going to be better at holding on to water and nutrients. We have a lot of the creatures that are involved in the soil community helping to aerate the soil. About 15 tons per acre of soil pass through earthworms each year. So their burrowing activity can help keep the soil looser. There are bacteria in the soil that can actually add nitrogen to the soil through nitrogen fixation. We talked about this when we talked about the nitrogen cycle. All right, one of our last characteristics of soil is thinking about how soils are structured vertically, so going from the surface down to the bedrock. And they are structured in these horizons. So we have like layers of soil existing going from the surface down to the bedrock. And depending on what area we're in, these soil profiles can look somewhat different. But in general, they're all structured in this way where they have an O horizon, A horizon, E horizon, B horizon, C horizon. Right? And the way we can remember this, O, A, E, B, C. You will have to remember this order. You can think oatmeal and eggs before coffee. So O horizon, A horizon, E horizon, B horizon. Let's talk about each of these different layers. So the O horizon is going to be dead organic matter. It's high in organic content. It's the primary source of energy for the soil community. It's where decomposition is happening a lot, and it's where we have this dark humus material at the top, right? So high in nutrients, a lot of decomposing plant matter. The A horizon, I think of this as like, so you can think O horizon organic, A horizon I think A plus, right? This is our A plus, like best layer of the soil. This is our topsoil. And this is where we have this optimal mixture of humus from the O horizon coming down, and then this leached mineral soil coming up. So optimal mixture of nutrients and minerals from above and below. And this is also where we're going to have root permeation from the overlying vegetation, which could be shallow or thick depending on the ecosystem. And the A horizon, since it's this optimal mixture of topsoil, it actually takes a really long time to develop. It only grows at a rate of 1 to 2 inches every 100 years. So if we deplete this topsoil, which is so important to vegetation growth, if we deplete that topsoil, it takes a long time for it to be replaced. We're going to come back to that later. The E horizon, E stands for eluviation, which means leaching. So this is where we have a process of leaching or dissolving away minerals due to this downward movement of water. So this horizon tends to be paler because those minerals are leaching, they're being moved by water through the soil in this spot. There's going to be less humus, and you're just going to be stuck with minerals that are resistant to that leaching. The B horizon is going to be our subsoil. This is where we're going to get accumulation of minerals that were leached from A and E. This layer of soil tends to be high in iron, calcium, aluminum, and some other minerals that are leached down through the soil and accumulate there. It tends to be higher in clay. It's usually reddish or yellow in color from oxidized metals that are accumulating in that subsoil. The sea horizon is where we get parent mineral material. So this would be like more your bedrock. So the original occupied site went through succession and that rock weathered away, and that weathering is then contributing to the soil production. This could be a good chance for you to quiz yourself. So see if you can remember the different layers and their orders, and then see if you can fill in what each layer means. So what is in each layer. And I'll let you pause the video and you can work on that. With these different soil layers, we can actually classify soils. It's called like soil taxonomy. We can put them into classifications based on what their soil profiles look like. So here are all of the different soil profile classifications, and we're just going to talk about a few of the more important ones. So one of the more important types of soil profiles are mollisols. These are fertile, dark soils, and we can see this really well-developed O and A horizon in these mollisols. So deep A horizon, really rich in humus and minerals. The precipitation in these, where these soils are found, is insufficient to really leach a lot of those minerals down to the E horizon. So these tend to be found in temperate grassland biomes, and you get this really nice A and O horizon developing because you have some precipitation, but not enough precipitation to really leach those minerals down. So these are actually going to be our best agricultural soils, and that's why, if you look at our map over here, that's why a lot of our farmland area is where those types of soils are found. Oxisols are going to be tropical and subtropical rainforests. We think about how much vegetation is in these forests, and we would imagine that there must be like this really well-developed A and O horizon, but there's actually not. So the A and O horizon in these is pretty thin. And that's because there's so much rain that we get so much leaching of those minerals down through the soil. And then also there's so much vegetation that as soon as nutrients are available, then they get sucked right back up by the vegetation. So in these tropical, subtropical rainforests, slash and burn agriculture is more prevalent, where a huge area of the forest is cut down and burned. That burning is then going to force nutrients back into the soil. And you can get a few years of crop growth from that, but it's relatively unsustainable because of the huge amount of leaching and the underdeveloped A and O horizon that exists in these soils. So they will slash and burn, grow for a few years, and then have to move on to another area. So it's a very unsustainable method of agriculture. Another example is alphasols. These are pretty widespread, moderately weathered forest soils. You can see on the map over here where they exist. These soils are not very deep, and they don't have really well-developed O, A, E, and B horizons, so they're only going to be suitable for agriculture if they're supplemented with organic matter or fertilizers. Aridisol, so arid means really dry, so these are going to be soils of drylands and deserts, and we can see that we get to rock very quickly. So here's where the bedrock is really starting in these soils, and then we have very little to no O and A horizon. This soil is relatively unstructured vertically. It looks pretty thin and light colored the whole way down. So there's going to be a really low amount of vegetation that's going to be able to exist in this soil. There's such high evaporation rates too that any salt that's in the soil is going to stay behind if it was in the water that was watering the soil, and it's going to result in like really salty soils. Spotosols are less common, but I thought it was interesting that this is the soil that we have in New Hampshire. So these are ashy, gray, more acidic soils. We tend to have sandier soils in New Hampshire. This has a strongly leached surface area, and you can actually see, like, here's that O and A horizon, but then you can see that those trails of leaching being pulled down through the soil here. So these are going to occur on coarse texture, like more acidic parent materials, really subject to leaching. These are found in moist to wet areas with a colder temperature. Hydric soils are pretty interesting, and they actually are a couple different categories. We have histosols and we have gelisols. These are both two different types of hydric soils. So the hist sols are where they're like a peatland or peat bog. So you have this buildup of undecayed vegetation. So these hydric soils tend to be more waterlogged, right? They're a waterlogged soil. So decomposition, decay is going to happen more slowly. And actually, when you have that not all the way decayed vegetation, this buildup of undecayed vegetation, it can contain a lot of energy. So if you take these peat soils and then you extract them and you dry them out, you can burn them and it provides a lot of energy. But it takes a long time for these soils to develop, so burning them is going to not be a sustainable practice. Gellisols are really similar, but they are permanently frozen at a depth. So this is going to be in areas where we have permafrost occurring. We can talk later about how when permafrost areas thaw, actually that's going to start increasing that rate of decay. That increasing rate of decay results in greenhouse gases, which is going to warm, which then creates more thaw, so that can become what we call a positive feedback loop. All right, that is it for soils for now, and so we'll be jumping into a soil lab with our eco columns next week.